So welcome to the Trustworthy Machine Learning lecture this year. My name is Jun, well, Song Juno, but usually I just put forward the middle part of my name because that's easier to pronounce. I'm leading a group on Scalable, Trustworthy AI at the University of Tübingen. So I like to kind of initiate the lecture by asking the question whether we are done with AI. So for example, 2 years ago when I started the first series of this lecture, I didn't ask this question with this OpenAI logo because there was no ChatGPT. But now people seem to wonder seriously whether AI is there, right? And there's no kind of additional expectation that we have for AI. But whether that is the case, right? So what do you think? Do you think we are done, or why are we sitting here? Maybe we can just use ChatGPT for everything and we are done. But I guess you also share the opinion that yeah, we are still not there, right? And there's some gap to be filled in, right? I believe so as well, and that's why I'm having this university group here working on kind of filling this gap, and also giving a lecture on trustworthy machine learning. So if the answer to this is yes, then I have some subsequent questions, although you didn't say yes. Why do we not see any kind of fundamental change in the way we do business? Well, we do see some changes in the businesses, right? But we don't see it in every possible business, right? For example, in medical domain, we don't see machine learning ML-based doctors anymore, not yet, right? And also, we don't really feel it in our daily life. We don't feel like, yeah, AI is really changing the way we do stuff in everyday life, and it's really introducing some quantum leap in the way we produce value. So now the question is, what is the remaining factors? What are remaining challenges that will get us there? So I like to kind of point out some of the limitations that we still have. One, AI is still very expensive. So let's say you're running a restaurant and you want to kind of predict the demand in the next few days. They like to use some ML-based prediction algorithm, forecasting algorithm for demand. But you know, like in order to do this, you need actually 3 factors. So one is human expertise, the other one is data, the other one is compute. They're all very expensive. So let's go for ML expertise first of all. Let's say you're trying to hire an ML engineer. They're very, very expensive, 100K per year still, right? And it's rising every year. And also, why are they so expensive, right? Because it takes a certain amount of education to get there, right? So if you want to do it by yourself, then you need to be educated properly for machine learning expertise. And that takes quite some time. You need to go to Coursera or go to a university for a couple of years to learn the basics and stuff, right? Well, there are ML Cloud nowadays, right? So you can go to ML Cloud and kind of rely on their services, right? But still, they're quite expensive to run services with ML-based cloud services. What about the data, right? The data is a tricky part because data is everywhere, but the data that you need is not very frequent. It's really hard to find the data that suits your need. So you're running a restaurant in a small town in some city, right? Small town in some city. Yeah. And then you have to kind of find the right data for your kind of business type and the type of restaurant even, and the kind of customers that you find in the vicinity, like whether there is a school around it, or depending on that, you will have different kind of customer background. So maybe you have to collect it by yourself, but to collect data by yourself, you need to know the data sets, database structure, and also it takes quite some time to collect the data, right? So collecting by yourself is quite expensive. If you use public data again, you don't find the right data for your application. Proprietary data, they're expensive and probably they're not suitable for your need. Well, I didn't talk about compute, but compute is, of course, very expensive. If you want to get 800 or 800 GPUs, even renting it for an hour could take like several tens of dollars. And if you do that for several days, then that could be super, super expensive. So yeah, of course, maybe you don't need such an expensive GPU, but still, you need to rent it from somewhere and pay for it. So now, let's say you have trained a model, right? Even if you have trained a model, the model may not work, right? You spend so much money, right? Several months and several thousands of euros on this model, and now the model does not work, right? Why? Because they tend to not generalize well when they are applied on a new situation. So that's one of the fundamental limitations that we have with AI models. And also, even if they, let's say they work, right? They're super generalizable, and you know, like we see close to 100% accuracy in some of the tasks that we test the model on. Even afterwards, there's something that's kind of missing between fully trustable system and the model that's working like 100% of the times on the test benchmark. What is it, right? So let's say your model is being used for systems that that has to do with your life or your health or your money, right? Then you have certain additional kind of hurdles against using this model with full trust. To kind of simulate this, how many of you can actually lift your hand in a self-driving car when the car is kind of driving along a cliff? Can you do it, right? Can you do it? Anyone? No? Okay. So I can't do it. And I think that's one of the key limitations that we have now. What about the medical decisions, right? Let's say a doctor says, an AI doctor says, you have a cancer, like stomach cancer, so you should start the therapy now. Are you going to trust it, right? Let's say like 10 different AI doctors say you have a cancer and should immediately start the treatment. Can I really start it, or do I at least want to talk to one human doctor to confirm if this is the case, right? So there's a certain gap, right, between a fully working kind of AI system and what humans can offer. But of course, the situation is a little bit different nowadays because of the foundational models, right? They are working super well, and also they're apparently trained on a huge amount of data. So maybe there's less problem with generalization because, you know, the model has seen a lot of things. So whatever you kind of give to the model, maybe it is quite likely that the model has seen it before, yeah? But still, you know, like with these foundation models, people still complain a lot about the limitations like hallucination and some safety issues. Like the model is so good that it recommends all kinds of weird stuff like how to build a bomb to start with, and a lot of kind of advice for criminal activities. And well, that's one part of the problem. The other part of the problem is, yeah, the model is working well, but now we have other problems like exposing the details in the training data, which is kind of a different nature, but still that's one of the problems with kind of deploying such a model at such a large scale. Yeah, so there's ChatGPT session that's running in some one of the countries, but now the model exposes some of the training data from some other random country, like the telephone number of a judge, right? Who made a decision to send somebody to jail, right? And then now the criminal, yeah. So forget about the countries. That was probably a bad example. So in one country, right? Let's say there's some public database that the ChatGPT has seen during training, and that includes one of the kind of personal details of a judge or prosecutor, right? Those people who may not want to put their personal information to public. And now the criminal kind of plays with ChatGPT and maybe I should try to find out the home address of the judge who sent me to jail. And then puts the name of this person and perhaps adds some other information in the ChatGPT session. And then boom, you get the home address of this person. How likely is that, right? Maybe that's not like super likely. You're not going to get this information like 100% of the time. But let's say you, for 0.01% of the cases, you get this information. Then that's already a huge leak in privacy, and that could potentially lead to serious consequences. So that's one issue with potentially kind of, yeah, even if AI is working super well, we should still work on some other problems. Yeah. Okay, so setting that aside, maybe let's come back to the lecture, which is Trustworthy AI. But we want to focus a little bit on 3 specific topics that I think are kind of central to the current machine learning. 1 is OD generalization, 2, explainability, and 3, uncertainty estimation. Yeah, you probably know what these really mean, right? OD generalization, you kind of generalize beyond the training data. Yeah, it explains by itself. Maybe what's interesting for the first lecture is what we are not covering in this lecture. One of them is fairness. Fairness is indeed very important because nowadays machine learning is applied for kind of making decisions that affects a person's life. Yeah, and there, if the decision is based on kind of features that that is legally unallowed for a system to use, or legally unethical or unethical to use, then we should have a control over kind of what kind of features the machine learning model can use to make this life-changing decision for the human. So that's about fairness, but we don't actually cover it for this lecture because I think there's quite a lot of overlap with the OD generalization part, where OD generalization is also deeply related to choosing the right features for making sure that it generalizes well to new situations. Privacy and security, this is also very important areas of research, but simply because it's a huge area, we don't really cover it in this lecture. Yeah, but these areas are gaining importance these days with the foundation models, which contains uncontrollable amount of data with uncontrollable amount of content. Abuse of AI tools, of course, with all these generative models, large generative models, people are creating fake data, like fake videos of interviews of some important figure, for example. And now these videos are getting less and less recognizable. Yeah. So how to detect these generated contents is becoming more important. Also, it matters for politics these days, right? Because yeah, people like to use this for political tools, right? Because they want to kind of denounce the other side of the politics, or they want to make fake news, right? Environmental concern is also quite important. On one side, we want to kind of address environmental issues with machine learning, but on the other side, we want to make sure that the usage of machine learning is not incurring damage in the environment in itself. So how to prevent overuse of machine learning GPUs? Because GPUs take up so much electricity, and to run these foundation models, they run on huge data centers, which is taking up a huge portion of the overall electricity usage around the globe. So By the way, if you have any question, you can always ask. Yeah. Governance, how to kind of set the regulations against the AI, or for the AI as well, because when there is no regulation as well, it's hard to kind of draw the boundary between what is possible and what is not possible. And sometimes people do not do it just because there's no regulation and it's not clear what is possible. So sometimes having a good regulation also moves things forward more quickly. Okay, so yeah, there are a lot of efforts already in the research domains towards trustworthy machine learning systems. So this is not the lecture which is supposed to be like pioneering the first attempt at trustworthiness. No, it's been there for several years. So if you look at some of the existing kind of domains in machine learning, for example, like privacy issues in language models and fair machine learning, membership inference, and so on. It's been there for quite some years, right? And even some of the domains are kind of losing its luster, right? So actually, OD generalization, if you look at it, it's kind of declining these days. But what I'm realizing is maybe the decline here is explained by kind of bifurcation or kind of diversification of the topic to other subdomains of OD generalization, such as test time adaptation, because test time adaptation is one kind of subdomain of OD generalization. But now you see it's gaining momentum. Of course, there's a bit of plateau at the moment, but maybe that's a noise. So the point is, it's been there for quite some time, right? So what is still missing in trustworthy machine learning? What do we need to contribute here? So the goal is, I'm not sure if you agree with me or not, but the goal for me personally is AI-led revolution, right? We want to really change the world to the better, right, using AI. But we are not there yet fully. We're kind of getting there. So how to close this gap? Yeah, so I want to kind of differentiate our approaches from the previous approaches in trustworthy machine learning by putting this single word scalable in front, right? So I want to make it more scalable and kind of, because when you look at a lot of work in this domain, trustworthy AI, many of them are focused on rather toyish data sets still. And I want to kind of scale this up to more relevant skills like GPT. So there's toy data. The benefit of toy data is that you can play around it. You can control the factors and see which factor is contributing to what effect and so on. So you have better understanding of how things work. But this is still not real data, because in real data, you really know, like, it's more relevant basically. So how can we approach this the scalable trustworthy machine learning, right? We can probably start with some toy data, of course. I would not recommend starting with real data, because each experiment there takes too much time for one thing, and also you don't really understand what's going on. So we can still start with some toy data, but I still want to kind of move on to scalable systems. So what we need to do is to understand the real reason why things are working in this toy case, and then carrying this knowledge to real world scenarios. So that's kind of the approach that I'm interested in, and we are trying to do at the group. There are some principles that I wish to talk about when it comes to scalability. So yeah, the methodology here makes sense, I guess. But also, I like something simple, right? I know simple is kind of hard to get into conferences, but still, I want to do something super, super simple, yeah, as much as possible. Because I've seen so many cases in machine learning where people try to come up with some complex systems, maybe just to get the paper in. But eventually, there's always this paper saying, yeah, you've done so many interesting stuff, but you know what? If you do it right, then actually the simplest baseline is doing the best job. Yeah, so that has happened in so many domains in machine learning, including OD generalization. So ERM is kind of the baseline where you just put this cross entropy loss and just train the model for several epochs, right? The usual kind of ImageNet training recipe. And that turns out to give not the worst. Actually, it's close to the best possible performance across the board, right? And whatever you do on top of it, complex training losses and funny things that you do with the data and so on, you don't actually get better than the simple baseline, right? So in the perspective of the practitioner who wants to kind of deploy a system in a new situation, what they are probably going to do is just to use the simple baseline of just training the system. And so that's kind of the, yeah, I've seen this pattern so many times in other domains. I can list them. I think I have some slide on this, maybe for the last lecture. That's another slide. So in deep metric learning as well, yeah, so from 2017, which is on the left side, to 2021, right? There has been this very good baseline in which is cross entropy loss function, and then they had so many complex loss functions for doing deep metric learning afterwards. But eventually, when you do the evaluation right, you're not beating the baseline significantly. So the lesson from all this, oh, well, that's actually my paper from some years ago. Here we also show that the baseline CAM is doing the best job compared to all the complex variants afterwards. So the pattern here is simply is probably the best, right? And we should probably not spend so much resources like research time and the compute on coming up with complex solutions for the sake of complexity. The second principle is we should understand before solving it, because typically I see that a lot of people just throw solutions at a problem, right? And yeah, maybe some of them works eventually. It also has to do with the scalability of the solution, right? The reason why we want to do take a look at the toy data set is because we want to understand what's going on. And based on the understanding, we can kind of move on to greater skills. Yeah. I think this is also very important. Let's not follow a dead end. So there are certain tasks in machine learning where you're supposed to work with a very limited amount of information. Yeah. Given this limited information, how far can you get? So this is kind of typical problem in machine learning. Yeah, but I feel like this kind of putting a kind of artificial limitation in how much information you're allowed to have is kind of putting a low upper bound on the performance or the utility that you can get out of this AI system. And I see that some of these tasks have dead end eventually. You're not going to get like a working system that's going to be useful in practice. And if I see that, I would say we should not do this task at all, right? Forget about this task, because regardless of how many years we put on this task, we're not going to get there, right? And we're not going to deploy this system in real life. So we don't have enough resources to kind of squander on this fake task. We need to really focus on something that's supposed to work in the long run. So the source of information, or the upper bound, I think is given by data in most cases. So I wish to kind of also share a bit of my philosophy on how I see data and how I see how we should progress in machine learning regarding data. Because when you take a look at many of the tasks in trustworthy machine learning, where you're required not just to do well on the given task, let's say classification, but also other stuff, where other stuff could be, you should generalize well to in distribution, but now you should also generalize well to out of distribution. So that's something else than what traditional machine learning is focused on. The other example is you should generalize well, of course, but also you need to give some explanation. So that's kind of a third task, or not third, another task on top of the original task. When it comes to uncertainty estimation, yes, you need to classify the image well, but on top of that, you should give good uncertainty estimation for the given prediction or for the given input. I would call this auxiliary task kind of machine learning 2.0, where machine learning 1.0 was all about predicting from x to y. Now we care about not just x to y function, but also x to z as well, or x to y to z, or x to z and y. Well, yeah, to me, these are all kind of similar. Eventually, you want to come up with something else than just x and y. But the problem is the kind of data that we are using for addressing these trustworthy machine learning systems are still based on the same kind of data as before. So we used to train the x to y function using xy pairs, right? But now we want to get z statistics, right, from x and y, also from just x and y data. I think there's a fundamental limitation here. And we should probably rethink about the data that's used for this trustworthy AI in the first place. Yeah, because I see that the current community is more focused on kind of fixing the data and still want to like squeeze the last bits of what we can get in terms of trustworthiness of learned models. So to visualize this idea, so let's say this is the status quo using XY data. I feel like there's a tiny kind of envelope, like tiny space around this current status quo by using the current kind of data. And that's kind of the upper bound that we are talking about. And this kind of fixing the data for solving a problem is so prevalent in machine learning that this is even called benchmarking, right? That's what benchmarking is. Benchmarking necessitates a fixed amount of resources for all the researchers. And it's basically building a challenge, right? So given the same resources, who can do the best, right? Of course, it's very fair, and that kind of ranks the methods in the right way. But there's a certain limitation of how well you can get in this case. So even if you reach like 100% here, you're probably not there. So I like to talk about new types of data, right? Because the upper bound that you can get using more data is, I think, much more interesting. And I like to call this more like a data hunting approach. It's like a dual problem. Previously, we wanted to maximize the performance of your model given data, right? So the constraint was the data, but now the constraint is you want to get very good system. You want to get like perfect, trustworthy system. And now the question is, how do you minimize the data collection cost for doing this? I think that's more interesting in my personal opinion, and that's also what I'm trying to push for. Another kind of viewpoint I want to share with you on data is, by the way, we're going to take a break in 50 minutes, is data as human knowledge. I like to view machine learning as human to computer interaction or interface. So eventually what's happening in machine learning is there's human knowledge and human way of doing things. We want to kind of transplant it in a computing machine, right? So that we can reproduce it more cheaply and also kind of automate it, basically. And the communication channel or the intermediate medium for this is data. So humans are generating data, and this data is kind of a means of communication between humans and machines. And now the data is in such a nicely understandable format for machine learning systems that you can do optimization on it, and then the machine learned model now kind of mimics what humans would do. And now there are two possible channels in general, not always, but in general, there are two possibilities how human knowledge could be transplanted to machine learning system. So one is, of course, annotations. So there will be a set of unlabeled data, which also involves a bit of kind of human knowledge as well. And now with this unlabeled data, there'll be like huge amount of data workers who comes in and produces labels. And by doing this, they are kind of recording their knowledge of what each image is basically, right? And this knowledge is now kind of transplanted to machine learning system through supervised learning. But there's another pathway, which is through the data machine learning engineer, controls the surrounding system around this training. So one example of how machine learning engineers' knowledge could be transplanted is by doing validations and design choices. So let's say the engineer decides to use sigmoid loss or binary cross-entropy loss instead of cross-entropy loss for training the system. What is the decision based on? By looking at the validation performance, for example. And then that's another way, human knowledge of what should be the best way to kind of train a model is impacting the final choice of the model. Yeah. Yeah, maybe that's not super clear yet. So I'll try to explain it the other way around. So I like to call the kind of crowdsourced knowledge and the huge annotation samples for training the model more suitable for kind of what supervision, which is kind of machine learning 1.0, where the task was to kind of replicate X to Y function. But usually when you look at the current trustworthy machine learning techniques, the gist of the method for increasing trustworthiness is not in the annotator side, but rather on the machine learning engineer or machine learning research side. They decide on the system, overall system, like the loss function or optimizer or how you compose data and so on. And these are kind of indirectly given to the machine learning model to enhance their trustworthiness. So what I'm basically questioning here is whether there should be a separation of information. Yeah. So annotators take care of the original task, and the machine learning researchers take care of the additional trustworthiness. I don't think that's ideal. I think what's potentially ideal is we also get all kinds of signals from annotators on enhancing the trustworthiness of the system. So annotators are not just giving what supervision in terms of, yeah, given X, what is Y, but also how, right? Why they think it's Y and how they reach the conclusion, right? So we can also collect this kind of information through, so I'm going to give you one example of how this could be done at ImageNet scale. That was actually one of my previous papers. So if you look at ImageNet annotation, what people do is annotate an image by clicking on the images containing the concept that you're looking for, like dog. And you record, yeah, this image is selected for the class dog, and this is dog, therefore. But what I'm suggesting, is we should probably collect huge amount of information that's kind of around it, such as the click location and how much time it took to reach the decision for this annotator. And these are examples of how signals that you can get from at a large scale. And maybe you can use this information at large scale. for example, by putting an auxiliary task along with the original task. And yeah, we show that it tends to improve the performance for the original task as well, and also lets it generalize well to new cases. That's one example. Another one is kind of nowadays people come with a terminology like process supervision or chain of thought distillation. Yeah, so how many of you have used GPT-01? Oh, okay. Yeah, you should try it out. It's super amazing. So how do the LLMs achieve such a good reasoning ability nowadays, right? They can solve math questions, although they didn't really solve the math questions that I tried. But the report says, yeah, it's much better than like a year before, of course. How this is possible is by exposing the models on all kinds of examples of reasoning that humans do, right? So you can get the thought processes of how humans approach a math problem by recording yeah, the solution, right? And giving them as a process supervision to language models. Or you can also generate kind of chain of thoughts. Do you know what chain of thought is? You all know? Okay. So you prompt the model with chain of thought. So you ask, you just don't give the question, but also ask it to kind of give the steps to reach the solution, right? And then use this information to train the next model. Like it's like a distillation. And so the point is we do see some paradigm towards this direction of training the model with greater exposure to the procedure for getting to the solution. More generally, I would like to call this paradigm as data-centric trustworthy AI. Well, that was a terminology that I came up with, but data-centric AI is an existing terminology. So what is data-centric AI? So if you look at machine learning research, many of them are talking about how to build a better architecture. Well, there used to be Transformer, but now people are talking about Mamba models, for example. There used to be AlexNet 10 years ago, but afterwards people came up with VGG and then ResNet and then VIT, yeah. So these are all about architecture. What about the loss function? People used to use simple, yeah, cross entropy, but afterwards people said, yeah, cross entropy is good, but maybe we should use focal loss to make it kind of generalize better, or and so on, right? Maybe augmentation as well, or other regularizations. People say, yeah, weight decay is good. Well, it's kind of underestimated how good it is, but now weight decay is super good. Or stuff like you should probably normalize the weights because that gives you better kind of generalization again. These are all questions about model-centric AI. How to change the model, how to change the training of the model to improve the system. But when it comes to practice and actually deploying the system in the real world, there is seldom a question about how to build a better model. You just download one of the models. And the bigger question is how to formulate the data in the right way to solve the problem better. Because data tends to matter much more than all other stuff. You can just use some reasonable model. And the rest of it boils down to just picking the right data, decision on where to source the data, how to annotate the data, how much diversity we need in the data, and how much money we should put into data, this kind of stuff. So I would say I don't want to like introduce a clear-cut boundary between the two, but there's model-centric side, and on the other spectrum we have data-centric side. And I would argue that what tends to matter more in practice is more data side of things. So I like to kind of I'm really focused on kind of making things work in real world. So I want to kind of push you slightly into the data-centric side as well. Now, the data-centric AI tends to matter more with foundation models, right? Because with foundation models, you're using like huge, billion scale, trillion scale foundation models. What can you change there, right? You don't want to change it, right? All you can do, perhaps, is to tune a small bit of this model to adapt to your problem with your data. So what matters nowadays more is how to select these few data points to run a few iterations on this fine-tuning of this language model to make it work in your problem. So yeah, I can see more emphasis in data-centric AI in this case nowadays. I'm glad we are focusing on more on this. Yeah. Okay, so with this, yeah, but I still didn't explain what data-centric trustworthy AI is. It's basically kind of using the same principle for kind of approaching the problems in trustworthy AI, the repetition of the same stuff that I talked about at the beginning. I'll quickly go over the current topics at the group in 3 minutes, and then take a break. So Alex from our group is working on diverse ensemble for OD generalization. So working on OD generalization, but one of the ways to achieve that is to train a diverse set of models and hoping that one of them is generalizing well to one of the environments. Yeah. So at test time, you need to pick the right model to generalize well. And we developed a system that's kind of scaling up better to ImageNet level, because previously everything seems to work only for a smaller scale data sets. So that's one example of scalability, of trustworthiness. Benjamin was a master's student last year who took the course, and he's now writing a thesis with us, and we are kind of working on generation of disagreement. So what he's trying to do is, given this kind of diverse ensemble, he's coming up with a data point which is going to incur the maximal disagreement among these models. Why is that useful? Because you want to kind of, given this sample, the models will respond in all kinds of different ways. Then what you can do is you can pick the model that's responding in the right way. Yeah. In this case, you only need to query all these models once with this specially formulated data, and that reduces the cost for making a decision on which model to use at test time. So that's one project that we're doing at Benjamin. Albert was also a master's student last year, and we are working on sourcing negative examples for improving image classifiers. So far, people have been using positive examples per class for training the system, but we are now trying to source hard negative samples for each class to improve the model for OD generalization as well. So that's also quite data-centric approach. Yes? So is anything which is not a positive sample? Yeah, that used to be the case, right? But we are also coming up with very specially generated negative samples for each class. So one example of that could be when you try to recognize a boat, yeah, usually the water pixels are kind of giving you a strong cue for recognizing the boat. And so as negative samples, we are producing water-only images without the boat. Yeah, so that's an example of negative. Alex is now also working on the question whether current foundation models, which are trained on huge amount of data, they are actually addressing all problems with spurious correlations and OD generalization, actually. So basically, he's asking the question: are we done with OD generalization given the foundation models? In this case, specifically foundational image segmentation models. Arnas is a PhD student. He's working on OD generalization as well. but is there a simple way to improve the baseline approach? So instead of using the last layer for achieving OD generalization to new context, is it actually better to use intermediate layers for achieving better generalization? The answer seems to be yes. And that's quite impactful because I would say everyone is using last layer for fine-tuning the model to generalize, to make it generalize better. But maybe we should consider lower layers. Arnas, again, is working on kind of data-centric view on compositional generalization. So compositional generalization means, let's say you see, yeah, we were talking about purple cat yesterday. So there's no such thing as purple cat. But now we want to kind of do well on this kind of new cases. But now if you think about it, purple is something that you have seen before in other contexts, right? Purple candy, or purple colored some other objects, right? And cat is also a known object from other contexts. It's just that this particular combination is new to you. So the question is, for achieving generalization to these kind of compositional new cases, do we actually need to feed such data to the model? Or is it more like once the model sees a lot of such new combinations, can it actually generalize better to even newer combinations later on? If so, what is the learning curve there? What is the what is the speed of conversions to this compositional generalization as you increase the number of compositions that you expose the model to? Darina was also a master's student last year. She's now working on clip embeddings and compositionality, because if you look at clip embeddings, the problem is the text encoder doesn't seem to understand what's going on. So for example, given this image, the clip variant seems to think it's more likely that the grass is eating the horse rather than the other way around. So trying to address this problem. Elisa is a PhD student, and she's working on human-centered training data attribution explanation. So training data attribution is asking the question, given a model behavior on certain data, what is the contributing data samples in the training data that makes the model behave in this way? That's very data-centric way of viewing explanation. And now she's working on how to make it more kind of closer to practice. So we did a lot of interviews on the participants who are working in industry and in science, and we asked the question whether they feel right about the current explanation methods, or they need some new techniques here. For this project, for the second project, Johannes, who is the tutor of this course, sitting there, he also joined as a co-author. Well, he was a master's student in this course from last year. Yeah. Evgeny was also another master's student from 2 years ago, the lecturer from 2 years ago. And he did some work on retrieval augmented generation, which is also very data-centric. So in ChatGPT kind of models, you do not ask for knowledge in the parametric kind of pre-trained model, but what you do is, given a query, you do some search in some database first, and then crawl some documents relevant to your query, and then based on the content of this query, you generate the answer. So you're not kind of attributing your answer back all the way back to parameters. Parameters are typically not interpretable, but you're attributing this back to the crawled documents. So now the answer from the language model is more trustable. And we had some project around it. Ankit is a PhD student in my group. He's working on data-centric representation comparison as well. So, and Anna, I'm going quickly now. Anna has worked on training data attribution for fairness. So let's say a model is not fair. Because of which data is it not fair? Yeah. She was also a master's student joining the course last year. For For uncertainty estimation, we also did some data-centric approaches where we trained a pre-trained model, which is giving you better uncertainty estimation in general. So you can just download the model and fine-tune this model for better uncertainty estimation. Balint was a master's student who joined the course 2 years ago, and he did very impressive work on kind of decomposing uncertainty estimation into algebraic uncertainty, epistemic uncertainty, and predictive uncertainty. And this is going to be presented at NeurIPS in 2 months, and it's got a spotlight presentation opportunity, which is super. Yeah. So this is a slide on the group web page. Again, it's repeating the same material as before. So now let's talk about the course. Some important information about the course. Tutors will be Johannes sitting there. Ankit. So Johannes will be in charge of the OD generalization part of the course. Ankit will be in charge of explainability part. And Lennart will be taking care of the uncertainty part. Unfortunately, Ankit and Lennart are not here today, but you will see them later on. Registration is needed because we need to collect your matriculation number and so on, right? So you can register on the link here. Your registration is finalized only when you complete the exercise 0. There's no minimal score for exercise 0, but you still need to submit it, yeah, to kind of conclude your registration. And also, exercise 0 is a good chance to kind of understand whether you have the prerequisite knowledge for this course. Schedule, we have it weekly. Yeah, so today is 17th October. Maybe can you close the door, please, in the back? Maybe there's some event outside. Yeah, this is lunchtime, so of course. So every week we have something until the 5th of December, and then we take a break until 9th of January when we resume the course. So basically, for the first 4 weeks, we're going to talk about OD generalization. In the middle of 4 weeks, we talk about explainability. And for the final part, we talk about uncertainty estimation after the break. And there will be tutorial sessions on the right. So Johannes will be kind of taking care of the exercise 1. But you know, like, so exercises are kind of distributed at the beginning of the topics. So exercise 1 will actually still be released next week on the lecture day. And then Johannes will introduce the exercise after the lecture next week. So there will be no tutorial today, actually. And then afterwards, I'll do a recap on exercise 0 for the tutorial session. And then you'll have 2 more sessions for recap for the exercise. And then there'll be grading of the exercise. And afterwards, you have kind of recap session for the exercise 1. Well, actually, you will have just 1 co-working session for exercise 1. But you're always welcome to ask questions on Discord. So for online Q&A, you can use Discord. For offline, you can come to the tutorial sessions. Yeah, and also you can ask questions to me before and after the lecture, of course, or on Discord. Yeah, so that's basically the structure. Tutorials will be held right after the lecture, basically, at the same place, in the same lecture hall here. Yeah. Lecture times, as you would have realized, it's from 12 to 14. There's web page. I recommend you take a look at the web page. Communication is done through email and Discord. Email for more private questions or requests. Yeah, but I recommend using Discord for Q&A because you probably want to share the question with the others, and others will like to also see the answer to the question. So I said, do not distribute the invitation code. Yeah, don't distribute it on the web. Don't put it on your social media. Grading policy, we have registration and exercise 0. That's going to complete your registration for the course. And for the exam, you also need to get more than 60% throughout the 3 exercises. And that's going to give you a ticket to the exam. And you'll take the exam, and you're going to get some score from your exam. And that will be combined with the exercise scores to kind of, well, put in the other way around. Your exercise scores will potentially give you extra bonus, like top-up points on top of your exercise score to make it into a final score. And based on the final score, we'll do the kind of thresholding to compute the final grade for your course. So that's kind of the function that we are implementing. There will be 2 exams. You can choose which exam to take, but if you take the exam 1 and if you pass it, then you cannot take exam 2. So, but if you take the exam 1 and fail, then you can take exam 2. Yeah, that's all I can say. Right. And how does the exercise top-up work? So yeah, you have to pass 60% to get the exam ticket. Let's say you get 10% point more, so you get 70% on average from the exercises, and your top-up will be the difference here, 10% point times 1/4. So you're going to add 2.5 percent points on top of your exam score. So maximum you can get 10% point more on your or your exam score. What if it goes beyond? What if you add this top up on top of your exam score? What if that goes beyond 100%? Then we cut it. Yeah. So if you do 100% on your exam, then you actually didn't need any exercise top up. You could have just got 60% from your exercise. Yeah. That's how it works. Yeah, for the final grade, we take into, it's hard to explain how we do it, but we also kind of try to make it fair against the other courses. And also we like to also spread the scores a bit in the course. Yeah, so the fairness is kind of the key here across the other courses, and also between you, and also taking into account the absolute difficulty of the exam as well, which is kind of hard to measure as well. Okay, disciplinary topics. Yeah, never happened, but still, I think quite important. Plagiarism is not good. Misuse of machine learning and data is not good. Free riders, yeah, because we have exercises in groups, so there may be some free riders in the exercises who don't turn up in your meetings, or doesn't contribute to anything, right? Then you can also report to us, and ideally with some evidence, right? And then we can kind of take care of the situation. We can probably give some 0 grades from the exercise for this person, or yeah, it depends on the situation. So I guess the message here is don't free ride, right? Do your work. Late submissions are no submissions. So there will be like time-wise strict deadline for the exercises. Please live up to that. Language models, right? Use of language models. This also includes like using Copilot for your code, or Cursor. I'm using Cursor these days, and it's super amazing. Please use it. Please use it. Also for writing your reports. But I want you to be transparent, right? So you can maybe write a few notes on what kind of language model you used for generating this. Um, and um, and also, like, I like to remark that when something goes wrong, right, you're kind of taking someone else's codes without proper crediting. Yeah, then that's not good, right? That's one example of plagiarism, right? When something like that happens, then you're held accountable, right? Not the cursor model, not the language model. You are the person who decides what to use in your submitted material. So um, you have to check. You have to be careful. Like there's minimal care that you have to take when you use these models. And also, maybe you want to kind of diversify it a little bit because when like you're so many people here, right? And if you use the same model, then you may actually end up having the same um, solutions, and that's also not good, right? Because we don't know whether you have copied each other's work, or you have come up with your original solution, or you have come up with the original prompt to the LLMs, right? So after getting the results from the LLM, I like you to kind of maybe personalize a bit further to kind of include your personal views or personal thoughts on it. I think that's also quite important these days. Okay, everything, yeah. What exactly constitutes misuse of data? Like taking someone else's private data, like GDPR, for example. So maybe something illegal regarding data. So if you take someone else's data without consent, something like that, then that's not good. So some other questions that we got from this year and last year. So what if you took the lecture last year and passed the 60% threshold for the exercises for the exam? Do they need to do the exercises again this year? No, we give you a choice. You can do it again to get the new grade from your exercises, or um, you just transfer the results from last year. But you have to choose now. Let me know if you don't say anything, then I will assume that you start anew. If you want to take it from the last year, then you have to tell me to know it. Because this is important because we need to formulate exercise groups, and the groups will be decided early on. If you decide later on that you do not want to do it, then, and also most likely you're not super committed as much as the others, right? Um, so I think it's better if you make the decision now, and you're then kind of exempt from all the exercises, and you will not be part of the group either. Yes. So we wouldn't have to do exercise 0 as well if we want to transfer one. Yeah, I haven't thought about it, but let's do it this way. Yeah. I'm not sure if there is such a case this year, but there were some exchange students last year who wanted to take exams remotely, but that's technically impossible, I would say. So um, if you're an exchange student, then I would recommend, yeah, you can take the lecture, you can take the course and watch the lecture on YouTube, but eventually you can take the oral exam once you return. Yeah. So for example, they took the oral exams like 2 weeks ago for the course last year, so even that is possible. Talking about exercise 0, please submit before this deadline here. These are like prerequisite materials for the course. Yeah, we also want to make sure that everyone is keen before they enter into exercise groups. So that's why we make sure. Yeah, because kind of submitting this exercise is kind of the minimal bar of your keenness, right? So if you are so less motivated and you don't even care about kind of submitting this empty exercise, then you're not registered and you're not part of the exercise groups. Okay, but exercise 0 does not count towards the final grade in any way, except for the fact that you have to submit it. Yes? I don't know if you mentioned it somewhere, but what is the minimum grade? 0. You just need to submit it. Yeah. But yeah, it's up to you. I mean, yeah, it's up to you. I tried my best to make sure that that covers the sufficient ground for the prerequisites. So please at least take a look. Yeah, and I'll do the grading as well, so you'll get the feedback. Yeah. Submitting an exercise. So for example, we switched to Kaggle from last year. So last year we used to use Colab, but we realized that Kaggle provides better GPUs for longer hours per month. So we're going to use it. How you do it, you copy and edit the notebook on your personal Kaggle account. You do the problems on your local kind of Kaggle account. Download it afterwards and send it to, you're going to get this Python notebook file. You send it to the email. Stay there, email. I had some struggle using Kaggle on the first day because I didn't know how to turn on the GPU. I learned it, and what you have to do is to verify your phone number. Yeah, once you verify your phone number after registering on Kaggle, then you can select your GPU on Settings Accelerator. And then, of course, you know all this, right? You have to do tensor.2 device to make sure that it runs on GPU. Yeah. You're going to get 30 P100 hours per week on Kaggle, which is not bad. So if you're a 3-person's team, then you're going to get 90 hours of P100 per week. Some FAQ as well. Can you use high-level libraries like scikit-learn or something like scikit-learn, train test fleet, or f.cross entropy? Can you use it? Where the question is actually to write a function for cross entropy, right? So you can't do it. You have to write it by yourself. But can you write? Yeah. But does that mean you have to write it without using any NumPy, right? That's also not true. You can use more basic libraries, but you should not use like one-line solution that's already implemented somewhere else. Yeah, I think you know what I mean by this, right? Yeah. Yeah, you don't need to implement np.random.choice. No. So there's a TML book as well for the course. It's unfortunately based on the materials from 2 years ago, mostly. Well, there has been an update last year as well, but most likely there won't be an update this year. So if you like, you can take a look at this book. Yeah, it was basically an effort led by Balint, who was a student from 2 years ago for this course. And this is an amazing book. But do not totally rely on this book because I think the materials have changed quite a bit. So for the final part of this today's lecture, I'm going to talk about some prerequisite materials that could be useful for exercise 0. I'm going to talk about multivariate calculus. There's a missing bullet point, probability theory, machine learning concepts, and PyTorch. I think many of you are just ready for this, but I just want to cover the ground to make sure that we are all starting from the same position. Although, like, talking about this for 20 minutes will not like bring you up to the same level, but at least I'm gonna. I still find it kind of useful, especially the multivariate calculus bits. And I would really appreciate it if you use it in your exams, for example, because that really reduces your chance of making mistakes regarding multivariate calculus. So the starting point is the Kronecker delta, which is a scalar depending on two variables, I and j. So if I is equal to j, then it's 1. If not, it's 0. It's very useful tool for doing multivariate calculus because let's say you derive a vector by itself, then what you get is a Kronecker delta. So this is a scalar way of writing down a multivariate calculus. So what's actually missing here is for all I and j. Yeah. So you're stating this I times j times. Yeah. But you're making a shorthand for that. You could have just written down, if you know this inverted triangle, right? You could have just written down inverted triangle, V subscript, and V, right, for writing this. And on the right side, you'll have I matrix for the identity matrix. That's one way to write it, but I like to write it in scalar fashion because that's more clear. More advanced problem. So what if you have a three-dimensional tensor, Vijk, and you like to, yeah, so you see it gets more complicated now, right? Because you can't write this easily with this inverted triangle. You're gonna write V, right? And you don't know how many dimensions V has, and it actually has three-dimensional indices. And now you're deriving this against another V, right? And on the right side, what should write down for this, right? I, Kronecker product I, Kronecker product I, but then how are the indices distributed in this case? It's a mess, right? So I like to bring all of them down to scalar expressions. And then it's much easier. So if you derive Vijk with respect to VABC, then you get the products of three deltas. Because the condition for this to be 1 is exactly when I is equal to A, J is equal to B, and K is equal to C. Yeah. So using this, we can do all kinds of stuff that you learn in multivariate calculus. So let's say C is a matrix product of A and B, which are also matrices. You can write down the matrix product like this. You all know this, right, from your linear algebra course. So Cij is sum over k, where k is the dummy index, Aik and Bjk. And now, oh, yeah, inverted triangle here, yeah. I call it del. Some people call it nabla if they're used to LaTeX. Whatever, right? I don't like it. So this inverted triangle f is a vector, right? If f is a scalar valued function based on some, it's a vector to scalar function. F is a vector to scalar function. Then this inverted triangle f is a vector of the same dimension as the input dimension, where you can write down each dimension of this vector as the derivative of f with respect to xi, ith index of the input. And now there's triangle as well. There's a specific name for this, Laplace, yeah, Laplace operator. Laplace operator for a vector to scalar function is actually a scalar. You sum over the second derivatives of each dimension, input dimension of f. Yeah, so these are some of the notations that you need to know. Yeah, so another rule that you need to know is sometimes the Kronecker delta could be eliminated from the equation when there's a summation. So let's say there's a sum over ij and q, and you see there's a delta ip here, right? And you realize that I here is actually one of the dummy indices that are summed over. Then what you can do is you remove this delta and you remove the I here and replace any occurrence of I in the rest of the equation with P. Yeah, why is that? Because you're summing over delta IP, right? So it's only 1 when I is equal to P, right? So summation over I is equal to kind of selecting I equals to P for the rest of the equation and kind of forget about the existence of delta or existence of summation over I in the rest of the equation. So below is another example. So let's say there's delta ij and sum over I, then you remove delta ij here, you remove sum over I, and replace every occurrence of I with j in the rest of the equation. So you're going to have xj squared log of sum over k, exp of a, it used to be ijk, but now it's jjk. Yeah. So using this, we can do all kinds of stuff like taking the derivative of the L2 norm of a vector. You can write out the L2 norm of the vector as the sum over the squares of every dimension of x. And then you take the derivative with respect to xi, right? So again, this is a vector, right? This is a vector. And you take the ith index of this vector. Then that's exactly this, where you take the derivative with respect to index I. And on the right side, you will have sum over xj squared, which is the L2 norm. You can swap the derivative here and summation because they're linear. And you can apply chain rule here. So you have 2xj, and now you have to derive xj with respect to xi. And now derivative of xj with respect to xi is delta ij. So you have delta ij here. And now you realize there's delta and there's summation. They cancel out each other. So you remove this delta ij, you remove this summation, and you replace j with I, you get 2xi. And you have 2xi here. So another way to write this down is this inverted triangle x norm squared, L2 norm squared is 2x. But instead of just writing that, you can also write down the ith element of this vector is 2xi for every I. Another proof we can do is you can derive a trace function with respect to its argument, input argument, where input argument is the matrix itself. What you get in this case is the identity matrix, actually. It's a constant gradient. So trace is a kind of a constant gradient function. But it's really hard to kind of visualize this when it comes to kind of derivative of a matrix valued function. For vector valued function, we have good imagination of what's happening, right? But matrix is an operator. How can you derive an operator, right? In that case, what you can do is to bring all of them down to earth and think in terms of scalars. So trace of A is just summation over A k k, where k is the dummy index. And you're interested in ijth element of this matrix. And you, again, swap the summation and derivative. And you get this multiplication of two delta functions, delta ik and delta jk. And you realize that one of the deltas can be removed, where k for the rest of the equation is replaced with I, and the summation goes away. And then you get delta ij again. Well, actually, you get delta ji, but actually delta ji and ij are identical. So you write down delta ij. And that's the scalar form of the matrix I. You can do something interesting as well, like taking the derivative of trace of AB with respect to A. It's an equivalent of taking the derivative xy with respect to x. And likewise, what you get is bji. So for scalar multiplications, when you derive xy with respect to x, then you get y, right? But in fact, in matrix valued functions, what you should get is actually y transpose. But y is a scalar, so transpose doesn't make sense anyways. But in in fact, if you generalize these to matrices, then you should get B transpose. Yeah, you have this quadratic form. It's called quadratic form, right? And it's a generalization of L to norm. Instead of just taking L to norm, you put some matrix A in between. So you're kind of doing some rotation before taking the L to norm or something like that. If you take the derivative of x of this quadratic form with respect to x, then what you get is A plus A transpose times x. Yeah, these are some exercises. So that's it for the multivariate calculus. All kinds of questions like if you know this Green's theorem or all kinds of multivariate calculus theorems, they also all boil down to these scalar forms, and it becomes easier to explain in that regime. Okay, now probability theory. I think you all know what random variable is, but who's from how to say, like non-quantitative background? Is there anyone from non-quantitative background, or maybe the right question is who didn't take any linear algebra course in your life? Okay, everyone took it. Good. Who didn't take any probability theory course in your life? Okay, so good. You probably know what random variable is then. But to make sure that you know, right, it's kind of an outcome of some random events, right? More precise definition, who's from math background, though? Who's from like pure maths and, okay, cool. So who knows measure theory? Oh, okay, cool. All right, so, okay. Yeah, it feels good. So random variable is actually a function, right? From some event space to some real valued space or complex valued or vector valued, yeah, whatever takes a value. So assuming that there's some random selection of some events, depending on that, your random variable is taking some value, right? It could be a discrete random variable, it could be continuous, or it could be a multivariate. It could be like a mixture of discrete and continuous as well. It could be anything, basically. But normally we talk about continuous random variables in many cases, which means there's underlying probability density function, which is continuous. So when your random variable is taking a value in continuous domain, then you can define a probability density function, which is written as px of x, where x is the random variable, and x is kind of the value that this large x is potentially taking. And the value of this function is defined in such a way that the real probability that we are interested in, for example, this random variable being inside some set in the value space. Let's say it's one-dimensional space, real value space, and let's say the event is the large x being between 1 and 3. Yeah. Then you can compute this simply by taking the integral over this density function p of x over the interval 1 and 3. Yeah. So that's how we define density function in an integral, indirect way. You can't really write down the full solution for this, really, given a random variable, but it's defined in such a way that if you want to evaluate this random variable probability of taking some value, then you can do integral over the density function to get this probability. P of x's may not actually be a function as well, right? It can also take values like infinity at a single point and so on. We call this density rather than a function, but for continuous random variables, we assume it's all smooth and nice function. Well, not smooth, it's measurable, not even measurable. may have some discontinuities. Like uniform distribution has discontinuities in the density, but still, yeah, it's continuous. And what's also important in machine learning is to understand the abuse of notation that people talk about a lot in their papers. Because when you write down the density function, you normally have to write down against which random variable are you writing this density function. So like you have to write px of y, right, to indicate, yeah, sorry, px of x, yeah, to indicate, yeah, this is for random variable x. And actually, what goes inside the argument of the function is a dummy variable, right? So you can also write px of y, and that also makes sense, although it's very confusing. So what abuse of notation here means is you can actually drop the this subscript x to indicate against which random variable are we talking about, right? And instead, we can just take a look at the form of the argument here to infer against which variable are we using, is this PDF defined. So the convention is to write p of y to indicate py of y, and pz for pz of z. Yeah. So we're going to adapt this notation as well. Yeah, some cumulative distribution function. You're basically interested in the value being below some value, the random variable being below some fixed value x. Yeah. That has to do with 1D continuous random variable. Expectation is the mean, right? You take the integral over the value itself, given that the density is given by the density function. Variance is x minus ex squared, and take the expectation of that. Standard deviation is the square root of that. Independence is quite important because that's a vague concept as well. In measure theory, it's a little bit more complicated how it's defined. But essentially, for the normal kind of random variables that we care about, like continuous random variables or multivariate continuous random variables, you can easily define it by saying x and y are independent if the event of x being somewhere and event of y being somewhere are kind of these probabilities, when you consider them together and when you consider them separately, are kind of multiplicatively defined. So the event of x being in A and y being in B together is the product of the probability of x being in A and the probability of y being in B. So essentially, if x and y are kind of occurring independently, then this holds, right? So it's very tautological, but that's another way to understand it. You throw a dice and you throw a coin, then the event of them happening like together is the same as the event them happening separately, and then take the product of them. Yeah, in PDF terms, it's much easier. You can just decompose the joint distribution into individual distributions, the product of individual distributions. Covariance is defined as very similarly to variance, but you're taking the product between x minus expectation of x and y minus expectation of y. You can also take values, negative values. And correlation is kind of a normalized version of covariance, where you, well, maybe the variance of x can be so much larger than variance of v. In that case, we probably have to normalize by the variance of x and y together to make sure that the values are in the right range. In this case, specifically, the values are in the range of -1 to 1. What is important is independence and covariance or correlation are kind of related concepts, but only one side of implication works. So if they are independent, then the covariance is 0, but not the other way around. Bayes' theorem is, you can basically invert the conditional probability. But when you invert the conditional probability, then you have to kind of do some correction of the priors for each of them. Yeah. So I like to call this, if you know contrapositive in logic, right? You A implies B, right? And then not B implies not A, right? That applies in logic. But this is like a probabilistic version of this contrapositive statement. So the probability of H given E is like, what's the probability of E implying H? Yeah. If that's 80%, then one could think maybe then the probability of not E, sorry, the probability of not H implying not E is probably also 80%, right? But that's not the case. You have to do some correction based on the standalone likelihood of H and E separately. That's what Bayes' theorem is giving you. That's another way to think about it. But on the other hand, no, forget about it. Yeah, don't have time. It also works for PDFs. Bayesian statistics. Yeah, typically we work with data, right? So what matters a lot for Bayesian statistics is to infer the probability of theta given all the observations x1 up to xn. But this can be inverted into p of x1 up to xn given theta, and then you do some correction. In this case, the correction is p of theta given p of x1 up to xn, but we normally just write c for this denominator because we don't normally care about it, because our interest is to recover theta. So we can write this, and since xi are kind of independent observations of the data, we can decompose them into products. So p of xi given theta up to p of xn given theta times the prior p theta. So we call this each of xi given theta as likelihood, and p of theta as prior, and the resulting resulting probability of distribution of theta given all the data as posterior. That's kind of the terminology we're using. Machine learning basics. Yeah, we don't have time for this, but generalization basically means you apply the rule to new situations. Yeah, let's skip it because we're going to talk about it a lot in the next lectures. Yeah, this one we will talk about it in the next lecture, so I'll skip it. Yeah, PyTorch, I can't teach you now. You try it with the exercise, and this is the feedback slide. So if you have any feedback, I'll flash these slides after every lecture. Each of these QR codes will lead to a different session, basically. So we collect feedback per lecture. So please, if you have any comments or requests or anything, just write to me through this form. It's anonymous. Okay, that's it for today. Thanks.